Good. Good morning, everyone. Can you hear me like this? Up to the right. So wonderful. Okay, great. So it's a pleasure to be here at this second edition of Athens NLP, which the first one took place in 2019, so 5 years ago. I was here already back then, so I'm happy to return to summer school. What do we do in this lecture today? So essentially, we look at sequences. Because, you know, it's all about sequences in NLP, if you think about, right? So it's sequences like here, the sentence, but then we might look at the sequences in words as well, or sequences in images, right? You can also treat images as a sequence, or speech symbol, speech input. So essentially, I would say most interesting data is essentially sequences. Sequences are everywhere. And what you have heard so far, so in the lecture by Ryan yesterday, you covered the fundamentals for processing, not really processing much of sequence data, but the fundamentals that we will take today and build up on. So you saw linear classifiers, and you touched already on the feed-forward neural networks. That's where I will take you further with. I also saw CNNs, and you talked about how to represent inputs. And the question we deal today with is how can we actually deal with sequences in first the traditional sense, and then building up to take everything from yesterday and going to deep neural networks and processing sequences in the encoder architecture. So this is what we're covering today. So it's going to be the fundamentals for, I would say, the building blocks of large language models today. We'll cover like the fundamentals at the beginning. We go back to language models. Now I'm wondering how many of you have heard of language models, the traditional Ngram language models already? Hands up. Yeah, like I expected this is to be a high fraction here, right? But we will take from there, connect it to yesterday, and then build up to go to more sequence sequence modeling models. To RNNs, attention, and then better representation, contextualized, to then spend quite some time on the transform architecture and how that works, which then gives us the background to look at pre-training, fine-tuning, prompting, and all these techniques that are nowadays, so to say, everywhere. But let me, actually, before I start, I want to go to this, I want you to go to this website, menti.com, and enter this code here. Let me just get here as well. So if you go to menti.com and enter this code, you can actually also scan this QR code if it's easier. Right. Great. Then let me ask you a question. I want to first get to know you a little bit better. And for that, where are you from? Wow, this is very, very nice mix of, yeah, of course, Greece, right? But I see also even the Netherlands, Denmark, Munich, Belgium, Stockholm, yeah, all over the place. Iran, right, nice, all right. Then what are you actually doing? I'm also wondering, do we have some bachelor students, master students here? Or most likely, a lot of PhD students, some faculty. All right, we do have some bachelor students, right? Even quite some industry here, right? Nice. And what did you do yesterday? Nice. Okay, none did none of the above. That was me actually traveling here. All right, great. All right, and I'm wondering, you had a lecture and a guest talk yesterday by Mirella Lapata. What is a takeaway that you learned already so far? What did you learn? Anything, also by talking to people. Right. Yes. Wonderful. Indeed. Quite a bit. Prompting is. What?
You need an LLM to summarize.
Yeah, you need an LLM. No, but it's really nice because we will touch up on quite some of these things today, right? And MLP is not enough. We need sequences. Prompting is not all you need, by Mirella. Adding structure important. Modularity, and of course, I saw anywhere. Academia likes nano LLMs, yeah. Great. Okay, I think this is it so far. Yes, then let me go back to my presentation slides. I will keep this open. I will get back to the Semanti every now and then. All right, good, then let's get started. I want to start with, in fact, you know this, NLP today is essentially LLMs everywhere. It's like this bulldozer that has entered our field, and we are now working mostly with LLMs. If I took a step back and just looked at recent research, so if I take the ACL conferences, which is the main venue of research for NLP, and just looking at titles of papers that talk about LLMs or related concepts, you see that nowadays, at the last conference in Bangkok, almost 50% of the papers had something with LLMs in their title. That's really impressive. But today we will see essentially, we will see the building blocks of LLMs in much more depth and look at this family of encoder-decoder models that you can think of. Indeed, you have some input that you want to represent, you need to encode it in some way, and then that goes on further and you want to do something with it. And most of the time in a language you want to decode to generate some output. But we will also touch upon this very general family a little bit in, you can do other things than just language. And that's the beauty also of today, that we can really bring very different modalities also together. And in this language school, you will hear much more about different modalities also later on. There will be a lecture on multimodality. There will be a lecture on really zooming into decoding and machine translation applications. So this picture comes back essentially probably in every lecture that follows from now on. But let me take you a little bit through a short history of NLP, because how did we get there to this bulldozer that we have today? Well, NLP started in the early 60s, so that's where also the term computational linguistics gets back to. And it started with symbolic approaches, meaning that people drafted rules and used symbolic AI in order to process language. So some of you might have heard about ELIZA. How many? You know this chatbot, right? Right. That was a symbolic approach. It was coded up, rule-based. I guess few know about Brill's to-speech tagger. It was a rule-based approach. No, probably not. This was how I somehow got into NLP back then, hearing about Brill. But the idea then was, hey, this doesn't scale. This is not enough. We also have a lot of exceptions in language, right? How do we deal with them? So the big shift was then to go to statistical approaches and look at, hey, actually, let's look at data. Let's look at data and collect statistics in order to process data or learn rules, learn grammars from data. And that's the first revolution or epoch where we moved to statistical NLP. And here a lot of algorithms come from, like structure prediction algorithms date back also to this epoch. And in this epoch, we also turned to use a lot of still feature engineering that also Ryan told you yesterday about, right? We were thinking about handcrafting these features and putting them into the model. And that was what I tried to represent here as this classic sparse n-hot encodings. After that came the emergence of deep learning. And that happened in early times in speech recognition, for instance. In 2010 already, we saw that there were really big gains in reduction of error rates by switching to RNNs, for instance, in speech processing. So they were a bit earlier than in NLP by applying RNNs there. Showing big gains. And another big area where deep neural networks had really impacted a lot was vision. So in around 2012, there was this big jump in error rates in object detection, where they switched to using CNNs to build these models. And this was very, very powerful for image classification, where you need to identify one of 1,000 objects. Okay? And in NLP, this was then happening a little bit later. So if you look at the NLP history again, we moved from symbolic processing then to statistical approaches where we had all this knowledge representation, statistical NLP, to handcrafted features. And then came the deep learning revolution. Around with 2015 was the year when deep learning really hit our field, where a lot of people were switching to using deep learning methods. So it's now, you can say, 10 years that we are essentially mostly using deep neural networks in NLP. And what happened is really that we moved to representation learning. You learn embeddings, and we were learning neural networks in the beginning a lot with RNN, CNN approaches to transformers, and they were then the building blocks for later models like multitask learning models and all the LLMs and pre-training that we have today. And this is not, you might think now, okay, this is a time when neural networks came to our field, right? But this is not the first time. There were approaches using neural nets before. And here is a nice quote by Eugene Charniak, which was also one of the pioneers in our field, who wrote a book in 2018 on Introduction to Deep Learning. And he, in his preface, said nicely, actually, it's the third time that neural nets have threatened a revolution, but it's really only the first time they deliver. So when I was doing my PhD, almost no one used neural networks. We were still using, support vector machine and the linear classifiers that you used yesterday in the lab. But then the thing took off, and we have then a whole area of multitask learning as well, where we try to combine neural networks, because essentially now you have nice pieces that you can combine. And so can you learn one model to do it all, essentially? That was a question we had already, say, 8 years ago. And the big explosion then happened once later on when we see now the pre-trained language model and the explosion of LLMs happening. So to sum up, NLP really loves deep learning nowadays. It's everywhere, and it's very, very powerful. Okay, great. But let me go back before we open this box more into the traditional language models. And this is now going to be a recap for most of you, but not all. So let me just go back to Menti for a moment and ask you to give me the next word. Oh, sorry, ignore the subheader. Is perhaps the best. Right. Space, large answer option. Yeah. Wonderful. So what we just did was essentially doing a language, what the language model is doing, predicting the next word. And here is an example of asking the same to Google Ngrams. What would be the next best word? And actually, it came up with pretty different words than you gave me now, right? Yeah, it's interesting to see. The best known, the best example, and indeed not just continuations, essentially. All right, so let's look deeper at LLMs and go from traditional LLMs over to neural LLMs, but the very early ones, and then bring it all the way up to using contextual embeddings. So language model technically is a model that gives you a probability distribution over word sequences. And what you can do with this is you can compute the probability of an entire sequence or text, like today is a great, what's the probability for the sequence? Or just to compute the probability of the next word. Today is a great, what's the likelihood that now, given this context, they would be the next most likely word. And formally, we can think of this as we have a sequence of input words that we want to then assign a probability distribution, a joint probability. And now the key idea is that we need to break this down, right? Or we need to work with this. So you can apply the chain rule to rewrite this joint probability as a conditional probability of the first word, then the second given the first, then the third given the first two, and so on. So we just rewrite the formula that we have done here, the probability of the next word given, notice, the first to the one before, so the entire sequence, right? Right, so we can think of this really as also generating, right, or, you know, at each time step, we look back at the history of the previous words, and so if you say generate the fourth word, you look back at the third and the second and all the way back, and so on. So this is how the language model is defined. Now, remember, this is conditioning then on the full history, right? And so if you have a sentence like an awesome summer school this year is happening in Athens, you know, we get quite a long history here, right? And this is indeed a problem for these models, and that's why in these traditional language models, a key assumption is that we need to make is this Markov assumption. Okay, what does it mean? How many of you remember this? Yeah, not so many. Yeah, quite okay. Maybe half of the people. So the key assumption here is that back then we needed to estimate these probabilities, right, by counting from corpora, but it's very hard if these sequences turn longer and longer. In fact, even for this very small example, it would be very challenging to get good probabilities. Why? Because what if one of them is 0, right? What happens then to this formula? It gives you 0 for the entire sequence. And so a common assumption in traditional language models is this Markov assumption, and that's the key idea here. So you have the sequence, right, the probability distribution over all the words, where this is just as we have defined it before, but now we approximate it, and that's the key idea, by assuming that we only look back not to the entire sequence from 1 up, but to the n-1 words before the current word that I'm predicting. Okay, so this is the idea. What does this mean? Well, if we have our chain rule here that we expand, we're essentially dropping history from this formula. So we're forgetting distant past. We just look back at a window before the current prediction. And this is then also called the nth order Markov assumption, where n means how much of the history do you take into account. So a first order Markov model would be 1 minus 1, 0, which means no history. Okay? All right. Indeed, is this valid for language? You might wonder. Not really, right? We are not really just ignoring the rest of the sentence that we heard when trying to predict the next one. Is it practical? Yes, very often. This was really foundational and used a lot, even in machine translation before neural deep learning came. So just a reminder, then how do we learn these parameters? We estimate them by counting from a corpus. So we collect statistics, we go over the corpus and say, now let's take a bigram model, so a history, order 2, which has a history of n-1, so 1 word. And now we are estimating what's the probability of a token given the previous one by just looking at, okay, if you have, for instance, 2 something, what is the likelihood of this bigram? You count how often this occurs in the corpus, and then normalize by the history. So here, 2, because you want to estimate what are all the likely next words following 2. Okay? Right. So just as a reminder, they have different orders. So the first order is the unigram or unigram language model. It has n-1, a history of 0, which look again, what does it mean? You do not look at any history. You really, each time you sample just from the distribution. You have a single distribution, like this one here, and you sample, say, words at a time. Okay? Notice that there are no connections between them in here. So you can sample what I just did by just repeatedly sampling from this distribution. In the biram language model, we have a history of 2, so n-1 words in the context. Now you see it again here. You have 1 word before. And now you have, if you want to have sample from this, you sample always conditioning what's the word before. So probability of city. What's the probability of center, giving that you have seen city before? Okay? And so we can think of this as, okay, we are sampling now the first one from that distribution. This is how it looks like in the beginning. And then once we have sampled one and once we are sampling the next one, we are sampling from the next distribution here, and so on and so on. And now we have these connections, but notice they only one connection at a time now. Okay. All right. So this is Engram's models, but while they were very, very powerful, they had a big issue, and that's sparsity, meaning we can't find good estimates for these probability estimations. So if the context gets longer, like here, its water is so W, you will have the problem that if, for instance, its water is so W never occurred in the corpus, even that engram that you try to estimate, you will get 0, right? And then the whole is 0. Or you might also have, you might also just not have the whole sequence. Sorry, you might not have the whole sequence, or you might not have the sequence for which you are trying to estimate the next word likelihood. So these are all sparsity problems that make this very problematic. But what do you do? And this increases as you increase the number of engrams size, right? If you have just bigrams, it's still okay. You likely get good estimates. But if you want to make better language models, then you want to condition on more history, and then you run into more sparsity problems. What can you do with this? One solution is combining different engram sizes, right? Think you have a bigram model, and now you don't know this bigram. What can you do? Well, I have maybe a unigram model and can back off, or a trigram and back off to a bigram model. That's what back off means. Conditional lower engrams, right? But key to this thing is, and that's what I want to go a little bit into, is smoothing. So we usually just don't use the exact counts as here. We need to deal with this unseen word problem in one way or another, and one big thing is smoothing. And what does this mean is that we, if we have words that we have not seen, we want to keep some of the probability mass for them. And how can we do this? Well, we essentially redistribute the probability mass so that it accounts for events that we haven't seen yet. Does that make sense? And how can we do this? We can try to change our counts. So if this is the count here for the words that we have seen, right? Denied the allegations, denied the reports, and so on, you get these distribution. But here, for charges, you wouldn't have any count, right? So you just pretend this is also applying, this is also happening, and allocate some mass to these other words. And how can you do this? A very simple way to do this is what's called +1 smoothing or Laplace smoothing, and that's you pretend that you saw each word one more time than what we did. Okay, so when you estimate the counts, then you just add 1 to all counts. So this is the formula we had before, and now we assume we counted one more, and same for the whole vocabulary size. So this is then giving you this picture here that you account for some mass. Okay? At least you have taken care of some of the problems that occur. All right. So this is a short recap of traditional language engram models. Remember 2 key things here. They have this Markov assumption, right? Are we all good with that now? Yeah. And the second thing is the probability estimates that we get. Yeah, we need to deal with them somehow, to deal with unseen words. And there is more to this. I'm not going. There's also unknown words and so on. But that's the key idea. Any questions at this point? Yeah?
Considering the Markov approach, I remember there was this magic when you also take into account the word class, so like syntactic.
Yeah.
Because now we are talking about like the probability of a word, after a word. And for example, if you hello, okay,
yeah.
Hi. And yes, in the case when you take also the syntactic features, for example, I don't know, you have a determiner, after determiner comes the most probably a noun or like an adjective, but never a verb, for example,
right.
Like the running is syntactically wrong. Don't you then eliminate like some cases and make it like more probable for
right.
other words?
Right.
Like what was this magic? I don't remember.
Right. Two things come to my mind now. One is you're already hinting at hidden Markov models where like when you do part-of-speech tagging or induction of part-of-speech tagging, where you condition this hidden class, and that then helps you generate. But there is also class-based language models that try to estimate these classes of words in order to exactly counterbalance this effect. There is extensions of these classical n-gram models that are just word-based, indeed. Yeah, that you probably have in mind here as well. Right. All right. Great. Okay. Yeah, there's one more here.
Yeah, I have a question which I think applies to both traditional language models and LLMs. The approach of generating one token at a time based on the history seems greedy, and it reminds me of the integer knapsack problem from algorithms, where every time you just make the choice that's next best.
Right.
But in algorithms, we also have dynamic programming where you get to generate many tokens in the future, and then you pick the best overall.
Right.
Is there something similar in NLP?
Yeah, that's a very good question. So indeed, there is dynamic programming algorithms in NLP, and indeed they would go and through. Even if you do the coding, you can do dynamic programming, or beam search, for instance, is an approximation. For the easiest, if I now think back, I don't know how many of you know part-of-speech tagging, right? That's the problem of assigning these word classes that we heard before. What's a verb, what's a noun, and so on. And there we also need to find the best sequence of hidden tags that generate the words. And here you will really want to have to maximize the sequence. You don't want to just greedy decoding what's the next best sequence, the next best tag that generated this word. And there we do like the Viterbi decoding algorithm. It's a very classic algorithm that actually goes through this lattice with dynamic programming.
I haven't seen that being applied to LLMs though.
No, but there is a decoding class that you will see more, you will hear more in decoding, who is giving Antonio in NT, in the MT lecture. Right.
Okay. Looking forward to it.
And decoders do use beam search, indeed. Yeah, indeed. But you can really, so the easiest is this greedy decoding that we just generate the next word at a time, given the previous one. And that's called greedy decoding. But usually we extend this a bit, where we say, don't just generate one word, but generate K words, and do this each time, and then from there on, you search for the best.
I assume that's more expensive though.
That's more indeed, it's more expensive. But as it turns out, like in machine translation, you can ask Antonis more about that, but in MT, in classical systems, they had a really huge beam. They wanted to decode, really, explore the space a lot. And with neural networks, this beam search has become 5 or much smaller, because there's much more power from the representations, probably, at least, yeah. All right, good. But now let's go to evaluating language models, because this is something that is very important as well. So how do we know, now we're estimating these parameters, how do we know that we have a good model, right? And so, think about even training your LLM. How do you estimate that it's a good LLM? Of course, there you have even more ways to look at it, but the simplest way is to look at, try to see how good it fits some holdout test data, okay? So you take some model the data hasn't seen during learning, that's important, right? You don't want to Because otherwise you think about the n-gram model and you test it on only data you have seen and you have no out-of-vocabulary words. It would be all very nice, and that's not realistic. So we need to take data it hasn't seen. And then we can think about two broad ways of doing evaluation. One is extrinsic, right? You would use this language. This means you would use it in some way down the line in your application, for instance, and test it through the application. Okay? So imagine you have a transcription system where you use a traditional LM and you plug it in and see how good your transcription system is working. So that's one way. But of course, it's not very easy, right? It's quite challenging to do this because you also need to have this transcription or downstream system in the first place. So the other way, in fact, is intrinsic evaluation. And that means doing the evaluation on the same task as you're building the model for. And since our task now is the language modeling task, how can we know how good it is, well, we ask how good can it actually estimate the probabilities on unseen data. Okay, that's what we are doing. So looking at how likely or how real is the data that we are gonna, how good are the probabilities assigned to this new data. And ideally, and this is actually a very general concept. This doesn't apply just to language models. Intrinsic versus extrinsic evaluation is a general machine learning idea. Ideally, these two correlate, right? If it's better intrinsically, then hopefully it helps you also in your application down the line. That's the idea. In reality, this is a little bit more complex, but still intrinsic validation is important, or is important, and you want to connect the two. So if we do the intrinsic evaluation, we're essentially playing again this game that we did before. So try to predict the next word, and now we're asking how well can we predict this next word. Okay, so when I ate pizza, I wipe off the I saw and so on. And you want to estimate it given, here you have a couple of next words with their probability estimates. Now, thinking back again, unigrams, right? Think about unigrams. They would be a terrible choice for this, right? Why? Let me just go back to Menti. Why would they be terrible at this game? Again, by now you know the answer, I think. Exactly, right, perfect. So they ignore everything that comes before, right? They don't look at the sequence or the history. They just randomly sample from the distribution. So no context is really the problem there. Right. So what can we do? And then to do evaluation, essentially we are looking at the probability that the model assigns to the sentences in this test data. And now this depends on the n-gram size that you have, right? You want to have a reasonable high n-gram language model. And with that, then we compute, given some data set, essentially estimate the likelihood of the sequence, and we normalize this in order to get these perplexity scores. Okay, that's the key idea. Essentially, it's very easy. You just get some data, apply your language model, and look at what's the perplexity of this data. Okay, how likely is this data under this model? Okay, so in practice, it looks like we are converting this into log space. You're taking the log of the probability of all the total number of words in your test data. And what this means is that now we're turning it around. So if this is lower, it's actually better. So low perplexity is good. Okay. Let me give you a little bit more intuition about this formula, because essentially you can think of this as a branching factor. Okay. What does this mean? If you now look back at the uniform model, uniform distribution, so a unigram language model, you would have, say, m sentences consisting of m random digits with a vocabulary, say, of 10. Okay, you have m digits. And if you do this perplexity calculation for this uniform distribution, right, then at each time step, you have 10 symbols, and you would randomly sample from these 10 symbols. Okay? If you do that and plug this into the formula, so you will have 1 over 10, and x log over 1 over 10, 2 to the log 2 of 2 to the power of 1, you're essentially getting a perplexity of 10 on this test sentence. And what does this mean now? In this sense, it's actually corresponding to the size of the vocabulary. That's like the branching factor that you have. Okay? So you can really think of this as a sort of equivalent to a branching factor. If you have a high perplexity, then you have a lot of possibilities, but you want to minimize that, because then you know, okay, the model actually knows what to predict next. Okay? All right. So if you look now at, and this is what essentially often when you see language models, they evaluate intrinsically on perplexity. Okay, so here is a graph of recent LMs that were tested on the Wall Street Journal test set, and you see that how these models got better and better by reducing their perplexity on this test set. Okay, but now, is this a good way to evaluate your language model again, right? What are we doing? We're trying to just look at the probabilities of this test set and trying to essentially fit the model well to this, right? It gives you an indication of, it should go down, essentially, if you train your model. That's the key thing, okay? All right, but later in the last part of this lecture, we will talk again on evaluation, because this is very simple, right? But is it good enough? Okay, all right. So then back to these language models in the traditional sense, I want to ask you two things. So there are some issues, and knowing everything you know so far, can traditional language models deal with these issues? Okay. So what about similar words like she bought a bicycle or she purchased a bicycle? Can an n-gram model deal with this? How many think yes? No? I don't know. No, not really, right? Think back. Can they share strengths around similar words? To very limiting degrees, right? In their world, every token is discrete, right? So they cannot really share the strength between, I mean, not as much as we would want them to do, okay? What about this? Long distance dependencies. So if you have a sentence like, for programming, she yesterday purchased her brand new laptop. Or for running, she yesterday purchased her brand new, right? These dependencies are quite far away now. Again, they cannot handle these long distance dependencies. Why? Markov assumption, right? We have this limited horizon. It's very hard to remember. You don't see this distance. All right, and that's why let's look now at neural language models and how hopefully they can help us solve or work towards solving these issues. Okay, let me just stop here if there's any question at this moment. No, then okay, great. So now a neural language model. So far we had counts, right? We estimated the counts. And we saw that they are brittle and they generalize poorly. So we added smoothing, for instance, to solve some of these problems. But it was always this, so we wanted to estimate this probability distribution here, right? Now the question is, can we use a neural network for this task? And the answer is indeed yes, we can do that. And what would it give us if we try to estimate this distribution now with a neural network instead of these count-based n-grams? Instead, you can think of this here, instead of these probability distributions that you get by counting, you can think of this now, okay, now we are plugging in a neural network that gives us the estimates for this probability distribution. Okay, we want to estimate these parameters. And how could we do this with a neural network? so far? Anyone? How could we do this? What could we use? What neural or let me rephrase. Did you see any neural network so far that you could use for this task, what you could imagine using for this task? Right? What are these? Remember? Yeah, multi-layer perceptrons, right? You heard yesterday. Now, can we use them for building a model that can do this? Yes, and that's what we're doing next. So let's essentially use now what you learned yesterday and recap what you learned yesterday in order to build a model that tries to estimate this say, trigram distribution. In fact, this is an idea that's quite old, again. So early neural network models, you already saw one, actually. Remember? You saw one already yesterday. Okay, I will get to that in the second slide. So one of the early one was the one by Banjo, called Neural Probabilistic Language Model. And what he did is he essentially built a neural network that takes the context of the t-1 words before, feeds this into a neural network, and tries to predict the vocabulary over what's the probability of this word given the context here. Okay? So essentially plugging in a feed-forward neural network, a multi-layer perceptron, in order to do this task. And so all these parameters here would then be this one here. Okay? Indeed, so you combine essentially a feed-forward neural network. You use still an engram, right? Why? Because you condition on the last three words here. But then you also use these distributed representations. So you add something more, which are these word vectors here, which we don't have in the traditional engram model. Okay? We'll get to that. So essentially, you can think of this now. I will show you this formula now, and then I will expand it later on in more detail. But what you can do is essentially plug in a neural network that takes in the, say, last two words now, embeds them, and runs them through the neural network in order to predict the softmax over y, which is the whole vocabulary, to predict the next token. Okay? All right. And we will see this, recap this in a minute so that it becomes clear. So the key idea here is that you have an embedding function that embeds these words. We will also see again, what does this mean? What is happening here at this stage? But say we embed the last two words, we concatenate them, and then we feed them through the first layer, and then a second layer in order to produce the y that we send to the softmax, which gives us the probability distribution of the y given the previous one. So you can then estimate these parameters by maximizing the log probability of this output here. And during inference, you use this network every time in order to estimate this probability distribution. All right, another, and I will get back to this in more detail, but just another LM that you have seen already yesterday is actually word2vec, right? If you think about that, it's also a language model. It's just a little bit different than the traditional engram model. Why? Because you're essentially trying to not, you still take a window like before, but you're not predicting the next word. You're predicting the one in the center. That's the skipgram model. Okay, so you're trying to predict the word in the center. You're from the word in the center, you're trying to predict the context words. So given Athens, what would be likely words in the context? That's one. But this original paper actually had two formulations where they also swapped it. So given this context, what's the likely word that appears in this context? That's the SIBO in this word2vec model. Right, so you can think of this again as a language model. Why? Because it's given a context now, the word, it tries to predict the surrounding context or vice versa. Okay? All right. So again, a feed-forward neural network, and in this word they used skipgrams because they are not consecutive. Okay, that's the idea. Now, let's go and just very briefly recap feed-forward neural networks. So what's a feed-forward neural network or a multi-layer perceptron? I will now show you a couple of different ways to look at it. So here is a graphical illustration. We have a set of inputs, we have a set of hidden layers, and we have a set of outputs. And indeed, what's the key characteristic of a feed-forward neural network is that it's fully connected, or dense. That you have every single neuron is connected to every other neural in before. So this one connects to everyone in the next, and all are fully connected. And that throughout the whole layers. You might have different number of layers, you might have different input layers, but the key is really this fully connected layers that you have. And indeed, they are also known as multi-layer perceptrons from a historical name that sticks. Okay. A key thing is that if we now zoom into this, let's say into this first block here, that we essentially do this computation at each of the layers. And what happens at this computation is essentially we are projecting this input here to the next layer, okay? And what is a crucial component here is that we projecting this through a nonlinearity. So what we take is, we take this input, we multiply it with the weights at the bias term, and then we still run it through this nonlinearity so that we are getting a nonlinear network. Okay? So let's look again. You can think of this now. I use here matrix notation, but you can really think of this as every weight, right? Doing the multiplication of the input with every of these weights. So all these here are the W here. And H minus 1 are all the nodes in the input, and then they give you, when you run it through this affine transformation, you get the HI, which is the output node. Okay? Now, a key thing to remember is that you need to have matching dimensions, right, in this computation, otherwise it wouldn't work. So if you have a H here of dimension D, Di, say here we have now 7, right, inputs, neurons. We would have a weight matrix of D times D in this case, or D times whatever is the output layer size. Sorry, vice versa. The output layer times the input dimensionality, okay? So in this case, we would have, let me just put it all, we would go from 7 dimensions to 9 dimensions. So the input has a dimensionality of Di, and we transform this into a 9-dimensional output representation. Okay? So you can think of this really as also not just this computation, but really as a projection of a vector in 7D to 9D. Okay? So that's, I really like to think of this in this way, so that you're extending your dimensionality from 7 to 9 by doing this Wx plus b, essentially. Okay? All right. Indeed, you can think of this as in a functional view. So each of these layer computations is a function that you're applying. And if you have a neural network like this one, you might have 2 functions, right, that you're applying to your input. So the first function is this one here, right, from the input with the first weight matrix to the hidden representation. And that's then, right, that's this function here that you feed it to the next function up there. Okay, so this is the functional point view. Or indeed, just to connect it back to the algebra, we can, see this, expand this again as we could take the input. Here is the first layer that we compute, and that's going to be sent then. So this is H1, and that's going to be sent with W2 forward to the second layer and giving you the output. Okay? Is it all good? Yeah, great. All right. Now, internally in the network, what's happening is actually a computational graph is built. Now, I don't remember if Ryan has talked about this yesterday. Did he a little bit? No? So internally, what is happening nowadays is essentially that you're building up, oh, this is not shown now. Oh, here is actually a gray box on my slides. What's happening is the model, the PyTorch and these toolkits build up a computational graph, which looks like following. So you have your operations. These are these circles here. And then you have parameters, but unfortunately, they are not shown on this screen. So I can, what this gives you, let me run through it. So you can think of this at each step in the computation, you're building up this graph. So you get X, you multiply it with W1. Then the next step is you add B1, right? And then the output of that is sent through a nonlinearity. And then you're essentially at this step here, right, in the computation. And then the computation goes on and takes W2, multiplies it with the output, adds P1, and then sends it to the second nonlinearity. And now imagine all of these ones here are gray, surrounded with a gray box, because this tells you that these are the parameters, the weights that are learned in the computational graph. While these all are functions that are applied to your inputs. Okay? Yeah, does it make sense? So behind the screen, this is happening, and this is also enabling the network then to do backpropagation because it builds up this graph and just follows this graph backwards to do backpropagation that you have seen yesterday. And why I'm telling you this, because in early NLP toolkits, you had to build up this graph by yourself. Okay, you had to build the connections. And if there is some problem in this graph, then you might run into issues, or there are some disconnections. Your model might behave very weirdly. Nowadays, toolkits take care a lot of this on their own, but if you ever go into changing internal states and so on, then you might want to know about this indeed. All right, good. So this is a neural network, exactly. This is the computational graph view. Now, what is X here, right? We didn't talk about this much. From Ryan, we heard about this can be sparse representations or n-hot features, but nowadays we really use a lot embeddings where we learn a representation for a word, right? And in fact, if you think about this word embeddings, so you have a matrix where for each word you have a d-dimensional vector that you learn, you essentially can think of this as v times d-dimensional lookup table, right? Given your vocabulary, for all of the words, you have a vector that you store in this table, and this is called the embedding layer or word lookup table. Okay? And why is this important? Because that's actually the building block in any of the transformer, right? You go from a word like yellow, you need to look up what's actually the index of this word, right? Each word is going to be mapped, or subword is going to be mapped to an index. So we can map this to a one-hot vector. And then this is going to be looked up in this embedding matrix. So essentially, for, say, the symbol like book, it has index this one here, the second row, essentially. And you can multiply these two to get out the embedding matrix, the embedding vector. And this is why this operation of looking up is very fast, right? You can look up several words at a time by just multiplying the one hot with the embedding matrix to get these dense representations out. Okay, does it make sense? Right, and now think of this embedding layer that Ryan was showing you already. Where does this sit in my computational graph? If I go back to this slide here, where do you think should this be? Huh? Yeah, right? We need to connect it to this one here, right? And now the key thing is, that we are connecting it such that it becomes a parameter of the model. Okay, that's the key. That's not just something we stick and just look up. We're actually learning these weights as well. And indeed, this is then how it looks. So you have an extra E. This is really this embedding matrix that you attach to your input. Now, I extended it by saying, okay, we use 2, but it could be just 1 as well. Okay, just as an example. But we connect it with this lookup function so that for a given word, we are querying this E, and then we're processing it. And now you see that this is really connected to the graph. And that's why if we backpropagate with some loss, we're actually also able to update the embedding matrix. Okay? Great. So this embedding layer is trained with the network, so you can think of this as essentially model parameters that we learn, and that's what's behind these neural language models in the early days. Okay? Right, now let's get back. I just want to show you a little bit more in detail. So I showed you these 2 language models. So this was the early one, right, by Banjo, right? So now we are just putting everything together. We have these embeddings. So we have the indices for the words that we look up, and we send them to a network and then produce an output. Okay? Or in Word2Vec, we would use, say, just one word and predict the context, or vice versa. So let me just go back here. How does this now look like? Let's put it all together. In this neural language model, we take now say 4 words. The students open there, right? And now we query the embedding matrix. So we go from words to 1 hot vectors, right? Each of them is an index. Look up the embedding for each of these words. Okay? We concatenate them, because now we are getting 4 words all the time, right? We concatenate them, and then we send them through this hidden layer. So here is now the concatenated representation. We send them through this hidden layer. We get the hidden representation for this input sequence. Okay? And from that input hidden representation, we are now trying to predict, okay, what's the next the word, most likely word, from all of the vocabulary. So now you have here a distribution which goes over all the vocabulary, and you are essentially projecting this hidden layer to this v-dimensional vector with u, and doing a softmax because you want a probability distribution out. Okay? And from there, then, we get, now, from this model, it would predict they open their books. Okay? And so now we have a window-based neural language model. Okay? So, and how does this work now? As the clock rang, the students opened there, and you can think of this now, okay, again, we are doing a window, right, a fixed length, and we now put this neural network on top, and that's then helping us to predict the next word. Okay, so now and then we're moving this further, and so on. Okay? All right. How do we train this? We essentially, what I just showed you, right? We ran this through a corpus and try to predict the next word at each time step with cross entropy, where we are taking the negative log likelihood, so the probability of the next word given the previous n-1 ones. And, but notice indeed, there are typically, this vocabulary size can be very, very, very huge. So there are some tricks to deal with this. For instance, negative sampling is one technique that Ryan told you about. You don't update the whole softmax, but you sample a negative word to make it more feasible. And in other things, tricks to make it more fast. But there's also, you know, now we often actually predict, if you go to machine translation, so we predict subwords, not full words as well. So there's other tricks, but that's the key idea. Okay, great. Now we have neural FNN language models. Do they now solve these issues? What about these issues we had, right? Can it handle similar words? Yes? No? Who thinks yes? Yeah, right? And why? What really helps us to do this? Yeah, the embeddings layer, exactly. What about long distance dependencies? No, right? We still not, they probably work better because the representation will capture a lot of this knowledge, but still we need to make this Markov assumption. And that's why, indeed, we need to go beyond this Markov assumption, beyond this window approach, right? Because if we don't have the Markov assumption, that means we are going back to the whole sequence, right? The whole sequence. Now, could we do this with the tools we already have? Actually. Could we do this? Do you think this could be possible with what you have seen so far? Yeah?
I guess yes, but it will be very demanding to go through the whole vocabulary.
Yeah, but how would you do this now? How would you do exactly? How could we, you know, what's the challenge if you think back? Now we have seen only feed-forward neural networks, right?
Make the window really long.
Yeah, you could, yeah, right. Right, that's what you meant, yeah, right. One solution, right, would be make the window very, very long, right? That's one way. But it's very challenging to train such a network, right? Yeah, go. Yeah, exactly. Or you go to some, but then we are changing, exactly, you're right. We could kind of perhaps move it to the hidden representation and try to get the history more into there. And that's what we are going to see next, exactly. That's the key idea of recurrent neural networks. But then we need to move away. Could we still do it with a feed-forward neural network? Technically. Right, we saw, yeah, we could extend it. Here I show you a crazy idea, which doesn't really work. But technically, we could treat it, the context, as a bag of words, right? And that's a bit of a crazy idea. I mean, so you could just treat everything, what you saw, you just observe it, and then it wouldn't matter how long it is. Meaning, okay, we would need to get the representation of, say, we would need to embed these words, right, in some way. But then again, we have a different amount of input embeddings, right? So I could get technically all the words before, no problem. I could query all their embeddings. But now the question is, what do I do with these embeddings? Okay, so a simple, let me see, a simple approach could be, do I not have it here? I thought I have it here. Ah, no, sorry, it is here. Sorry, I just didn't look at it. A very simple approach could be, indeed, just get all previous from 1 to I words, embed them, average them, and send it through the same network. And what would we have now? Wow, we would have a neural language model with a multi-layer perceptron, which doesn't have the Markov assumption, right? Because it's not restricted to any input length. But what we're doing here is creating an average or a summed representation of all the words, which is a bag of words assumption, right? Would it matter how we input the words? No, it wouldn't, right? So why would indeed this be a terrible idea? Let me go back to Samantha and ask you there. No, no, I didn't. Sorry, switching back. Why would this be a terrible idea? No context, right? No sequence information, bag of words. It would not order matters in language a lot, right? So if I have, it was not good, it was actually quite bad, right? Versus, it was not bad, it was actually quite good, right? That's very different meanings that we would want to convey. And in this model, it would be giving the same representation, okay? This would maybe not work, this average representation, I will get back to that, is very good for text categorization. So if you do text classification, it might be actually quite good to just average your word embeddings. But for many tasks like language modeling, then you really want to know, if you say predictors words, what has been said before in sequence, and not just as a bag of words assumption. All right. So indeed, the problems we had is the fixed input, right? We had to deal with it in some way. And what we just did, and the order that we are losing, essentially. But language is really productive, and that's why it's so interesting to model it, because we can add more things to a sentence to make it more rich, and this makes it difficult to work with neural networks, like feed-forward neural networks that actually assume this fixed length input, which is not such a good fit for language. And you have already seen 2 ways or 3 ways to deal with this. So you could, in fact, truncate it to a fixed k or make it long to a certain k, right? Or you could use just average embeddings that we just saw. Indeed, I'll just show you this again. So the key idea would be, if you have the sentence, you get all the embeddings and you averaged in some way, and then you send that averaged representation, summing or averaging, into your neural network, because then you're getting rid of this problem of fixed size input. And you can think of this as a pooling operation that you have seen in CNNs. But still, remember, this is really like a bag of words. You don't look at the order. Okay? So better ways to deal with variable length inputs are indeed 2 model families. One is the convolutional neural network that you have seen by Ryan, right? So you have essentially a CNN that walks over your input in space, essentially, and then combines these pieces into something that's of fixed size, and you can then input to your neural network, okay? Or you can go to a recurrent neural network, which we will see next, okay? Yeah, there's a question over there.
Yeah, before we move on to the recurrent neural network, could we solve the problem of order by including positional encodings like we do in transformer?
Yeah, exactly. And that's the thing that's indeed the idea of position encodings is exactly for that, to get back order into transformers.
But they can technically apply to MLPs.
Yeah, but a transformer in a sense is an MLP, but with attention and position encodings. Yeah, exactly. All, you see these pieces that we are talking about today are really deep pieces that go into the transformer architecture. Exactly.
I think the question is, could you use the positional embeddings when you do the averaging?
Yeah, why not? You could also, yeah, you could also do it, but yeah, probably someone has done it, I guess. I would guess. But yeah, how strong the signal? Yeah, you could do it probably. Yeah, you can for sure. Yeah, you could try.
Maybe nobody thought to use it back then, or we were using MLPs to solve the problem.
Yeah, exactly, because you didn't. Either you went to one of these 2 model families, right, to solve sequences, or used other approaches. I mean, going back to this one, if you have an application where it's just about text classification, where some strong, some words are very important and the order is not so important, then this provides actually quite strong baselines in some of these applications, especially if you need a fast model. Yeah.
Machine translation was not something that was solvable at that time, so nobody really cared about orders.
Right, but you could. In fact, the position embedding is essentially nowadays an embedding, a lookup layer that you that you add, or some function that you embed to. But we will see this later. Okay, right. So, in order to deal with this problem that you have longer sequences, you go either to the CNNs, right, and then you have a convolution of a certain size that goes over the input. This you can think as kind of a soft n-grams, actually. Why? Because in the CNN, you still have to define what's your filter size, okay? And you can think of this like n-grams that go over your sequence and produce an output. And that's then averaged and fed forward. So here you have a filter of size. This is your filter, which takes 3 embeddings and produces an output. And this is a parameter that you need to set in your CNN. So you have a k of 3, and you then run this over your sequence. And depending on how long your sequence is, you will get these output embeddings here, But then you need to transform them back into a fixed sequence, and what does the CNN do? It does pooling, which means extracting for each of these dimensions, say the maximum or the pooling operation defines what is extracted, but it summarizes these representations into one layer that then sent further. And usually you have a lot of these filters so that you cover different sizes. Okay? Does it make sense to call them soft n-grams? Right? They are like n-grams, but then they went through a neural network with nonlinearities and everything. So it's kind of computing, computing some representation over an n-gram. All right. Let me get started with, or let me actually ask you if there's still some questions here. All right. Then let me just get started with RNNs before we go into the break. I want to give you the key idea, the basic key idea, and then do the advanced RNNs after the break, and then go to contextualized representations. All right, so recurrent neural networks are a family of neural networks. And they are indeed very good at modeling variable length inputs. So, what they are very good at is modeling sequences or order information that other models like the averaging of embeddings doesn't do. And they are very good also at dealing with long distance dependencies. And the key thing is that they indeed, by doing so, they don't need to make this Markov assumption. Okay, so we can now get to a model which is able to process the entire input, and this input can be of variable length. Okay? Now the question is, how can this model do this? And here is the key idea in a simple visualization. So on the left, what you see is the standard vanilla feed-forward neural network. And you have some input, you have some hidden representation, and you have some output. Okay? The key addition of the RNN is that it has this additional error here. It has an additional recurrence link. Okay? And as you see, this is something that operates on the hidden layer. Okay? It adds a link on the hidden layer. And what does this mean? It's essentially keeping information in this hidden layer, so that what we heard before, right, is implemented in this model. And you can think of this as a kind of memory state that is embedded in the hidden layer. Why? Because it has this recurrence link. It looks back to the past. And that's why it acts like a sort of memory. But now the key distinguishing feature is that an RNN is really a stepwise model. So what this means is when we take an RNN, we process a sequence one step at a time. Okay? Meaning, given some sequence X, we apply this network at every time step T. Okay? So now what we get is it takes an input at step T, and it processes this through this RNN. Okay? And what this means is that we are taking the previous state and the current input. So we take not only the input that we have at this stage, at time step T, but also the previous state, and combine the two. So we really take the current input X and the previous state, which is coming from here, that we then take care of in order to produce the next new state. Okay? This is different from here, because here we just take X and send it through the network, right? Not one step at a time. Here we send the whole sequence through the network. Okay? So let's look at this a little bit more. So what is this recurrence link? It's essentially another set of parameters that you add to your model. So you have the input weights, the output weights, and now you have this additional matrix U, which is the recurrence connections. And if you expand this, you can see this here as you have your input, you have your weight which is here, input weights. And now when you go to the hidden layer, in the feed-forward neural network, you would just go this way, right? You would just send it through the network to produce the output, but in the recurrent neural network, you additionally have the previous time step and this additional parameter u that you have. And this together creates a link between the hidden layers. So now you indeed add this u with the previous time hidden dimension into the equation in order to forward it. And that's the key idea of an RNN. Okay? Let's look at this, because at this time step is indeed the key thing here. We get a sequence, but now we produce, at the first time step, we get like an I. We run it through the RNN input, we get the hidden representation and some output. And now we get the next word, and I run it again through this network, and you see now that it's not just the next word that I'm getting, but I'm also getting the previous state in order to compute the current state, okay? And so on. And so the next one, again, I get the next input, and I have this connection back to the hidden representation. Okay, then I do some output, and then the last one. Okay, so now I have four states that I processed one step at a time. So the core idea is now that you do share the parameter of the networks over time. Okay, make sense? With each time step, in each of these computations, you would apply this U matrix inside the recurrence, but also the other two matrices at input and output. Okay? And you can think of this as two functions again. One is the recurrence function and one is the output function. And so I'm going now to use a notation by Goldberg. You can think of an RNN as given an input sequence of vectors, it processes this input sequence going from some start state, right, because it's a time model. It applies a recurrence function that consumes the input and the previous time state. And then you decide if you also have an output function that maps the current state to some output. Okay? So you have recurrence, which computes these two. With these two computes the next new state. And from the next new state, you might have an output function that gives you some output. And then the next state. Okay? So this abstraction, you can see it again here. You have from a sequence of inputs and the starting state, you apply the recurrence function to produce the next state. And from that, you can produce the output state. And so you can think of this really as, you at each time step get an input and then build up this network. And building up this network means, or is called unrolling it over time. Okay? And now again, you see that these parameters are all shared throughout this sequence. Okay, does that make sense? Again, here we look at let's look at this state 4. Why does it depend on all the previous states? Because we would apply the recurrence operation given the current input x4 and the previous state s3. But what is this S3? S3 is actually depending on the previous recurrence, right? It's depending on the previous inputs and the previous hidden state. And now again, what is the previous hidden state? We essentially expand it all the way down to that the current recurrence operation on this input actually depends on all the previous recurrence operations on the previous inputs and the previous states. Yeah? All right. Great. And now, how do we train this network? And that's the key bottleneck in a way as well. We need to unroll this network. We need to really send all the inputs to the sequence, and then we only can observe the loss and backpropagate to the network. Okay, we need to build up the sequence because we have this recurrence operation. It all depends on the whole sequence. The benefit now is that we can give it any sequence length, right? It's no longer restricted. And they are all connected, so we keep also the order information. And so the algorithm for doing this is called backpropagation through time, which essentially unrolls this network and then does backpropagation through this network. So it's an unrolled computational graph that we can backpropagate, and you can, in fact, tie the parameters because you reuse them over time. In this way, you reduce the parameters, and you can model arbitrary input lengths. Right. So again, just to recap, this would be if you have a sequence with the FN feed-forward neural network, we need to somehow deal with the problem that they're in different input sizes, so we can just average them. Note that this is also sometimes called continuous bag of words, because now we use word embeddings that we average. And the same sequence in RNN's way would be processed as follows, right? Remember, here we feed the whole sequence in as one averaged representation. And here we do this stepwise. So we get the sequence, we compute the first hidden state, we go to the next, we compute the next, we go forward, and we go to the last state. And this is the RNN's way of processing this sequence with the shared parameters. And now you can think of this actually as a vector that kind of connects or represents the entire sequence, right? So this last state is also called the sentence, or sometimes was referred to as the thought vector, which is kind of a summary of the sentence, or the encoder representation, okay? All right, and with this now, we can also use it as a language model, right? We saw language models now in at least 4 different ways. Here is a 5th way, and this is an RNN's way, where we change the representation of the network to an RNN, which would get the word as input, have the cell, and then compute the likely next word as output. Okay, and now, given this output, we would feed it into the next state and say, okay, you've seen now so long, what's the next likely word? And the network would predict and we would get a recurrent neural network language model. Okay, does that make sense? Right. So what about these issues again? Can we handle this? Yes, we have solved it already, right? We have embeddings now that help us to get good representations for similar words. What about long-distance dependencies? Yes, we can also handle them quite well. And this is, I think, time for a break, because we will see that the vanilla RNN is still not yet very good at this, but that's the question for the next part. So just a summary, we have seen LMs now that predict the next words, and then we went to RNNs that can model any input length, and then you can actually also produce outputs, but I will go into this next. RNNs are great, and they can be used for a lot of things. We saw now the basics of RNNs. It's a family of neural networks, and I want to show you next that... yeah, right. I want to tell you that the slides are also on the website, so if you want to go through the slides as well, you can download them now. All right, so we saw RNNs, and they have these 2 functions, right? The recurrence and the output operation. And I put here that they can optionally produce an output at each time step, TO. Essentially, with RNNs, what you get is a very flexible model. You can essentially see it as kind of almost a plug-and-play model, and it was used as this before transformers. RNNs were the thing to work with. And I show you just next, okay, how can you use this model? And for some common usage patterns, to think of how to use them. Right, so you can use an RNN as an acceptor, right? Which means that you are not interested in predicting some output at each time step, but you're maybe just predicting, say, a sentiment for a sentence. Okay, you are interested in one label. So in that case, a typical scenario is just to run the sequence through your RNN and fetch the last state and use that for your prediction, right? We saw now that this last state is actually capturing the whole sequence, right? So you are encoding it and using it as an acceptor for some y. Now, how you use this as an acceptor is again up to you. You can decide, okay, I use the last state. But maybe for your application you want to somehow still pool over different other previous states. You could also do so. There are some models that do that. So you can pool over the different hidden states. In fact, this is what we're gonna see very soon, which is kind of an idea which is very close to what's attention doing. You can think of an RNN also as an encoder. So instead of saying I'm interested in predicting some label here, I can use this into some other application. So just use the RNN as giving me a representation, an encoding of the sequence. And so why? Because maybe you run an RNN like at some level and use it as a tool or modular piece in another bigger model. And an example of this could be to run your RNN over characters and then feed it forward to something that handles words and so on, hierarchies. Okay. You can use it also as transducer. So we saw acceptor, encoder, and transducer. And transducer really means at each time step you want to predict something. So input transducing to some output. This is typical if you would use an RNN for, say, part-of-speech tagging, predicting word classes for each input word, or named entity recognition, where you also want to predict at each time step. So then it's called transducer. Or you could use it as a generator. So you're using some input and use the RNN not to encode, but to generate a sequence. Okay? You could do that as well, and use the RNN in the output. So for instance, for image caption generation, in fact, the early image caption generation models were using an image, feeding it through a CNN, and then the output of the CNN is going to be the initialization for the RNN. So you would get the image encoding from the CNN, and then initialize your start state here with this representation and train the model. Okay, now I actually want to have a caption for this image, and you train an RNN on top. You see, you're combining different models. Now a CNN and an RNN, or RNNs with several. So it's kind of like plug and play, right, that you get. Or you can think of encoder-decoder models, or also called sequence-to-sequence models. So sequence-to-sequence models are a special type of encoder-decoder model where you get an input sequence, you run the RNN through that input sequence, and then you have a generation step where you generate an output sequence. And they can be of different lengths as well. And we see this in more future. You see that you get a very flexible type of neural network here. I want to show you a couple of more concepts which are important because we will see them back later. And I want to introduce them here in the framework of RNNs because it's very intuitive. So imagine you have this sentence here, right? The person who, okay, I don't read it out loud on purpose for you to read it. Okay? What does this sentence mean? Okay? But if you read from left to right, you might have a little bit first difficulties in reading this sentence, right? It's called the garden path sentence. It's on purpose difficult to read. But if you read it, so is it the person who hunts ducks out on weekends, or the person who hunts ducks out on the weekends, right? Yeah, you see. So if I know what's coming afterwards, this helps me read the sentence, right? And so a very prevalent idea is also to not just use the left to right sequence, but also right to left sequence. So if I am now at this stage, what's happening here? Let me just try again. Yeah, no, it's my thing, sorry. So if I go back and I'm at this stage, I'm trying to process the sentence, right? Hunts here. I process it from left to right, but if I also process it from right to left, then I might have more information, so I can actually use both directions as inputs for my, say, I'm predicting part-of-speech tag, or I'm predicting the word, or I'm whatever task I'm doing. And this notion is called bidirectional RNN, because we are running it in forward and backward direction over the sequence. Okay? Notice now in this model, at this time step here, you would only have this sequence up to here and that sequence up to here, right? And these two are then fed other hidden representations. So you wouldn't have these ones here yet. They would be then the next generation step. Okay? Does it make sense? Right. So bidirectional or bidirectionality is a concept to know. Stacking is another concept, because now these are bidirectional RNNs or LSTMs, whatever. So you run a sequence in forward and backward pass. You get two representations. But why not make it deeper, right? Why not stack several RNN layers on top of each other, right? So that's the idea of stacking. And indeed, people have tried to add more layers. It helped to some degree, but it doesn't, it then follows off. You add too much parameters, it doesn't help scaling up too deeply as well. But also stacking in the sense of putting another RNN on the top, on the bottom, which here in this model, for instance, you have a model that goes over the letters first, so a bidirectional LSTM on the letter level, and that gives you a representation, and also a word embedding layer, and you could boost both as input to the model. Right now you're stacking not only layers, but actually modules. Okay? Okay, and indeed that's then the idea of using subword representations that you can use. And this is very useful for instance, in multilinguality, if you have languages which are morphologically rich, you can look at the character representations, and they, for instance, for part-of-speech tagging, give you a lot of cues. Like if the word is ending in this able sequence, it's most likely an adjective. If a word starts with by in Danish, it's most likely a noun, some sort of information that you can leverage. All right, good. So we have bidirectionality, we have stacking, we have also something called residual connections. And the idea of a residual connection is because if you stack a lot of layers, be it RNN layers or feed-forward neural layers, it becomes very difficult to train this network. And so, because also the gradients that flow through become very small. The solution of residual connection is actually to add direct connections back to your input at different layers. So residual connection is essentially you're adding the input again at different layers. So here you have the input, you run it through your function, but then, so you get an f of x, right? But you later on again add the input again to the network at higher levels. Okay, so it's kind of adding the input again at different layers. And that helps the learning of the network. So indeed, this is also what we see in transformers are using residual connections, but they date back to at least 2015. Here in ResNets they were used. So where they went up to really, I think, 30 layers or 50 layers in early papers almost 10 years ago already. Okay, right, good. Then these are important building blocks. Now I will go to the gated variants because there is a problem with the vanilla RNN that we have seen so far. It's essentially too simple to work well with long sequences. That's why the RNN we saw is like this cookie, and now we're adding a little bit of sugar to these ones to get a bit more powerful models, and they are called GRU and LSTM. I will show you the idea with the GRU and very quickly go over LSTMs, because the idea is similar in the two. But why, if you run and train RNNs, you get this problem of vanishing gradients. So if you go through the network, you need to unfold it over time, right? And when you then get the loss in the beginning, it will be very large. But as you go back, this loss it might diminish and be very tiny, especially if the sequence is gonna be very, very long. And so that's why there has been an idea of enriching these cells so that they keep more information during the process, okay? And that's called gating, or gated RNNs. So what are gated RNNs? And what's the key idea? We here have again the vanilla RNN that we just saw, right? We have an input, previous state. It does some computation and then creates a new hidden state. Maybe we have an output. Here we have an output O function as well. So here is our input recurrent operation that gets us the new state. But look that the new state is essentially rewritten, right? If, as we get the previous one, we are essentially forwarding a new HT completely. So the idea of gating is to keep a dynamic memory or keep some of the information or choose at every time step t whether what we are actually forwarding. Okay? So what the gating does is it has a little a gate that controls the flow in the cell, and we are computing this gate in order to see how much of this internal memory, candidate memory, we will use. And the GRU, which was devised by Cho in 2014, will give you now the idea in a simplified manner. So we are looking at generating a candidate cell. So we are computing a new hidden, so let me take C now instead of H, which becomes clear later on. So let's take C as the hidden representation. And we are interested in computing a new candidate for C. How do we do this? In the same manner as before. Okay? But what now comes into place is this gating function. What does it do? It takes, again, also the input and the previous state, but it sends it to a sigmoid, which is like a gate, saying, gives you back a scalar, a number, telling you how much it will use for this thing. So it gives you back a scalar which says, okay, how much do I want to update this cell? And with this cell, with this update gate, what you computed, you essentially then define what's going to be your next hidden state. How do you do this? By applying this gate to the candidate that you just computed or the previous state. So you're deciding how much of the current output do I take in versus how much of the previous one do I take in by computing this update gate. Okay? So this is like a scalar that does element-wise multiplication of all the values in your candidate vector versus 1 minus the scalar, so deciding how much do I choose the new candidate or the previous one in order to compute the new CT. Okay? And with this, it says you essentially, if my gamma that I get is bigger than 0, then I use more information from the current computation, and otherwise I rely more on the previous one. So it gates the information in the cell. Okay? All right. Is this clear? Yeah? Right, great. The GRU is still a little bit more complex than this, but the idea is the same. You have these gates that compute a score that decide on how much of the flow is going through. But in the full GRU, we have actually 2 gates, not just one. And so we have one, which is this update gate that we just saw. So this is the same as before. We are computing how much we want to update the new cell. So here, right? And then we decide also how much we want to rely on the previous one. But here it also looks at how much do I actually keep from the previous cell. So it has this reset gate, which again takes the current input and the previous one and computes another gate, another score that says, okay, the candidate is now no longer just the one we had before, but we are here deciding how much of the previous content we are actually feeding forward to the network. So that's the reset gate. Okay, so we are computing this reset gate in order to decide how much goes into the candidate, and then combine these two to get the update. And how does this help us? Because this is now helping us to make it easier to retain or retrain information. So you have this explicit gating mechanism in the cells that helps you keep track of, helps the network to learn better. over time. So the GRU has these 2 gates. The LSTM instead has 3 gates. It's a bit more complex. And another key feature is that it has a memory cell and a hidden state, so two things flow through the network. But for now, it's essentially enough to know LSTM is a more complex variant of the GRU. It has gates. It has more gates. It was invented by Sepp Hochreiter and Jürgen Schmidhuber. And it looks like this. So it has the C before that we saw, but also the H. And it has the forget gate, the input gate, and the output gate. So how much do I forget of the previous cell? How much do I actually move into this computation? And how much do I write out in order to keep the information flow? Okay, so now we don't longer have just H minus T minus 1, but all these computations in the cells. Okay? All right, so here are the details if you want to look at it. But I will go forward, and now you might wonder, which one is better, right? GRU or LSTM? GRU is more efficient. It has fewer parameters. There is no conclusive evidence that one is always better than the other. It's more like an empirical question. So people have used GRUs, switched to LSTMs. LSTMs are typically a good starting choice, but if you need less computation, then a GRU is faster and more efficient. So to summarize, we have now RNNs and 2 fancy variants, LSTM and GRU. They add this gating mechanism, and we saw, and they help us train longer networks because they retain information. And we also saw other concepts in this space, bidirectionality stacking and residual connections. And next we want to go to representations and then glue it all together with attention and so on. Okay, all right, any questions? No, let's go further then into attention. All right, indeed, this is a very important concept because the next big model is all about attention, right? It's essentially an attention-based network. So what is attention? The motivation of attention comes from MT, essentially. And in MT, you have a source sentence, like here, this German sentence, that you can encode in some way. Here we use an RNN. And then the basic idea of an encoder-decoder neural machine translation model was to then feed this representation to a decoder and do decoding. Okay? So at each time step, you decode the next target token. Now, and you will hear more about this in the lecture by Antonis. But what we're looking now is, okay, in this framework, we know now that the RNN gives us this sentence vector, right? This is kind of the summary of this source sentence. And in the original formulation, from that sentence vector, the network had to learn the translation, right? It was all essentially a single vector that did the magic in a way, almost, right? So we feed this sentence vector into the decoder, and from there decode the language, the target language. But it turns out that this is really difficult also again with longer sequences. And there is a very famous quote by Ray Mooney who said, you can't cram the meaning of a whole sentence into a single vector. Okay? Right. Indeed, can we do better? That was the key idea, the key question. Can we do better than cramming this all into one vector? Well, essentially, we did take the last encoder, an encoding state, right, H4 here, but we essentially do have all the previous encoder states as well, right? So how could we use them? And that's where then the idea of attention came from. When we generate the next word in MT, why don't we just look back at the previous states as well in the encoder? Okay? So going back to our example here, why are we just looking at this and not at all of these were vectors before? Okay? And that's the key idea. So the attention's core idea is that at one time step in the decoding process, we are actually looking back at the encoder states. And so what it does is there are a couple of concepts that we are now introducing. It looks at, this one here is called the query vector. So the one that you're currently, you are decoding time steps t. And these are called the key vectors. And now you're comparing the query with all of the key vectors. Okay? And so how does it look like? At time step t, remember this is at every time step this happens, but we are looking now at just one. You do a pairwise comparison of the query with each of the key vectors. And why that? Because you want to find a way that when I generate the next token, how can I kind of combine the information from this query vectors, the key vectors to help me do the decoding. Yeah? So we compare all pairwise query key pairs, we normalize them, and then get these attention scores out that we use in order to get the new state. Okay, so get the new C. Let's look at this in more detail. For each query and key, we calculate a score. We want to essentially match query and key and compute a similarity, some score. And we need for that some function A that gives us this score. So let's call this attention score function. And so we take the query vector and the key vector and compute some score, A1. We do the same for the next and all the others as well. And now we get attention scores, right? But they are not yet, they're just scores. They can be also negative. And so since we want to use them as a weight, we actually normalize these scores. And for that, we use the softmax function. So what happens now is we run these values through the softmax, and this gives us back a probability distribution. Okay, converting the scores to, okay, the first one seems to be the highest, gets the highest what's called attention score. Okay? All right? Let me actually pause here for a second. Is this okay? Right. Now, I want to just go quickly to, no, let me go that afterwards. To my slide. What do we do now with these attention weights? Because they are now a distribution. Essentially, what they give us is how important each of the vectors is. And now we take them and we call them value vectors and combine them linearly. So we weight them in order to get a new CT. Okay, so we are actually computing them, taking them as weights. Oops, sorry. No. So we are taking the linear weighted combination of the value vectors and combining them with the weights we just computed in order to get a weighted representation of the input vectors. Yeah? All right? Okay. This is the key idea of attention. Now, again, recap, you want to have this weighted combination of the key vectors given a query. You get the attention scores, and the key thing is to normalize them to get these weights, but you then use this in the network to do the decoding. So what you would now do is use this new CT in the decoder instead of the original one. Okay? But notice that this attention score A can be anything, and you have very different functions that you could apply to calculate the similarity. Okay? Well, let me stop here just a second and go to the Menti, because I want to ask you, what's an advantage of using a softmax in the attention calculation? Why do we use softmax? And I show you back the slide here. What could be an advantage? Can be many, several. Oh. Is it now showing? No. Let me show. Let's try if it works. Now? Okay, great. All right. Yeah, wonderful. Yeah, great. So you see you get, first of all, you get a probability distribution, right? It's positive, it's sums to 1, but it also helps the calculation at optimization because you're getting very small numbers. You essentially get a smooth output, indeed a smooth probability distribution. That helps you again. Yeah, okay, comparable attention scores, also true. Yeah, wonderful, great. And we don't have any zero probabilities, yes, wonderful. All right, good. So there are several, now in the original one, I didn't give you the function that calculates the attention scores because there is in the literature actually a lot of different ones. So there was a nice paper by Luang et al. In 2015 that tried to compare different attention scoring functions for machine translation, and they came up with, for instance, also just the dot product, or a bilinear function where you have a weight matrix. But the thing is, or the one before uses an entire nonlinearity feed-forward neural network. But it turns out that the dot product is very simple and powerful because it has no parameters, right? You don't need to learn yet another parameter function. And indeed, in the scaled, this is also then the transform architecture uses a scaled dot product. So internally uses the dot product, but then also normalizes them by sequence length. And so this is what happens internally. So the main idea is there is a lot of choice, yet again, but sometimes simple things work well. I don't know, they probably found this by trying around a lot of ways, but this is what they do it. Okay, great, then let me just recap. We saw now recurrent neural networks, right? We have an encoder and decoder, and now we have attention weights that when we decode, look back at our encoding states and give us information about what to attend to in the input sequence. And with this, we can then do decoding. And notice this way of using attention is called encoder-decoder attention, right? Why? Because we look at the encoder and the decoder, or it's also called cross-attention because you have these two, you look across encoder-decoders. Why is this important? Or let me show you, because this attention is essentially giving you information about, for instance, if you look at machine translation, if you translate French to English, then one of these rows now, columns now, is essentially what we just did, the attention computation. So what we just did is this calculation of the weights. And you see now that if when you translate accord to agreement, it pays a lot of attention to this word here. But you also see that, yeah, it's hard to see, but here it's a little bit non-black, that when you do this word here, it also looks at this one here, the zone, in the economic zone, and so on. So these were like a little bit inspired by word alignment matrices that you did in early MT, where you try to learn this word by word links explicitly, which now the network trains for you. So you're learning these alignments between words where you have multiple, you can align one word can be aligned to multiple. Here you see it more nicely. Signed is aligned to the two words here via these attention scores. Okay? Right. And the big thing that came with this using attention is shown in this original paper. So these are two graphs that are coming from this original paper from 2015, which show, first of all, these attention scores, what they learn. But they also showed this graph. So here you have an RNN, where you see if you don't use attention, you get problems translating longer sequences. And when you use attention, they had really good improvements on handling longer sequences as well. Okay? This was a very influential paper back then. And so attention is a very important concept because it can help us deal with sequences. And we saw cross-attention, but there's also a notion of self-attention. What if we just change, instead of source to target, we just try to attend to the same sequence? Okay, that's called self-attention, where we have the sequence itself and try to attend to, okay, what are you looking at when you decode the sequence from the previous part of the sequence? Okay? And that's coming back again as an important concept in contrast to cross-attention that goes across the decoder-encoder. Attention is also something that's used in computer vision. For instance, in image caption generation, there is a famous paper that looked at the attention when you if you think of the image as a matrix and which pixel to attend to. Here you see that what is the current pixel part that the network paid a lot of attention to. Okay, all right, all good? Any questions on attention so far? All clear? Yeah, go ahead.
No more question. I noticed that you use the words query, and key. When they first proposed the attention, I don't think that they use those terms. I think those came later with the transformer, but it's a good transition. It's a good idea.
Yes, exactly, because I already called the hidden representations value vectors then, right, yes, exactly. Right, all right, no good, we saw now attention. I just want to go to contextual representations before going to the transformer, because this is putting everything together that we saw so far. So traditional word embeddings are like this, right? But again, what's missing? Context, exactly. There is no context, right? If you look at this picture, we purposely drew the two vectors the same, right? If you take them from word to vec, they would be the same. But we want word representations that distinguish a Danish from Danish, right? And so Elmo is one of the seminal papers to start a new era of representations called contextualized embeddings, where the key idea is you learn a word token vector, not type vector like in word2vec. You learn a contextualized representation that depends on the context around the use. And so ELMO stands for Embeddings from Language Models. It's a self-supervised pre-trained RNN-based encoder. And it was introduced by Peters et al. From Google 2018. And here is one snapshot of their paper. So our representations differ from traditional word type embeddings. So these are, again, these embedding from word2vec or other ways to get them. In that each token is assigned a representation that is a function of the entire input sentence. Okay? So it's essentially a language encoder that gives you good word representations. How did they do this? They went all the way down to characters to generate these token embeddings. And how did they do this? The embeddings from language model looks like this. Back to our example, imagine now we are trying to get a good representation of this word ducks. here. We run it through the network, which as first step actually looks at all the characters. So there is a convolutional neural network in Elmo that goes over the character sequences and gives you a representation of the word from the convolutional neural net. Okay? So this is like a stacked model. You have a CNN on the bottom that works over the characters. Then from that representation, you have a LSTM that you run over, and this is a bidirectional LSTM. Okay, so get an LSTM, and meaning now DAX, we run it in both directions. You get two representations. And it's not yet there yet because it's a deep neural network. And so what they did is they stacked several bi-LSTM layers on top of each other. I don't remember now how many indeed, 3 or 4. And each of those is going to give you another representation of the word in context, right? And now the question is, what do you use in the end? Because now you have built up this whole network. And what they did is essentially they took the representation at the different layers, and they learn a weight over them. And that's then the combination of this weighted sum of the embeddings of the words at different layers gives you the Elmo representation for the word DAX in this sentence. Yeah? And so now we get a contextualized token embedding that captures all this information from the Elmo network. Yeah? Yeah?
So the Elmo DAX vector is what the word DAX means in that context.
Exactly, and that's the key. This is really not just a lookup, right, that you do, but this is a representation of this word DAX in this context. Yeah, that's the key. You could also, perhaps they used it, I don't remember now, they used the CNN to get the word representation, but there you could use the static embeddings for DAX in that learned way. Yeah. But the key is really, this DAX, if you run it through another sentence, this vector over here is different, depending on what sentence you're using. Indeed, so you have an LSTM that goes over both directions, and you have several layers, indeed, L layers, and this gives you, you also have the input embedding layer. Actually, you have also these embeddings at the input layer. So you get two because you have a bidirectional plus 1 representation. So which one to use? They did this learning and combination by all layer weights, but they also show that it's very good to just use the top layer. You know, again, it's a network. You have a lot of information where you can pick out informations and choose what you want to use. That's the key message here, essentially. How to train it? Now, it trains again on word sequences. It trains on entire sentences and predicts each token using its context. Then we again have a softmax layer at the top and uses the entire sequence. So it's also using the bidirectionality. Remember, in context to word, in contrast, word to vec trains word by word. It uses the context during training, but not when you use the model. Then you just have static word embeddings. Okay? And so indeed, if you train this model at this time step for Danish, you would have this setup and try to predict Danish in this context here. I will skip this. The key thing was that this was one of the very powerful models that showed us that we can gain quite a bit of improvement over very different tasks. So this was 2018. It was also, if you look at this slide, so this shows the NLP progress for named entity recognition over the last many years. But you see here that there was a sudden jump up, and this was indeed due to Elmo using contextualized representations, and DAC-LM was a predecessor of Elmo. And then you see also here, you see LSTM, CNN, CRFs, they were used before, but with static embeddings, not these contextualized ones. So they help you a lot in proving involvements. And then came transformer-based models that can also be very useful. But, you know, like FLAIR is an RNN-based model, it's also still very good for an identity recognition. So it's not said that transformer is all you need all the time, essentially. All right, I will skip this slide here. But again, what is a limitation of an RNN? Because Elmo is really an RNN, right, type of model. What's a limitation here? It's a very powerful model, but yeah, sequential training, right? Because when you train this model, you need to unfold the whole sequence, all the layers. So you have a huge model, a huge computational cost to train it. And that's where we are getting now to transformers. Okay. All right. So transformer is really a revolution in NLP, but beyond. And we will look now at the high-level architecture and the main concepts in the transformer architecture. This is also called a fully attentional network. And I thank Arianna for creating a lot of the slides that I'm using now. So the core idea is that attention is all you need, and this is also the title of the original paper that proposed the transformer architecture. And the idea came out from the observation that attention is really, really powerful. So attention really helped MT and had a lot of impact. But on the other hand, recurrency in RNNs is a main obstacle, as we just heard. So the question is, can we build a fully attentional sequence-to-sequence model without recurrency? Okay? And so the main idea here was, instead of having the RNN with all the connections and the unrolling, can we just, given a state, use attention to look back at the other states in order to do this? Okay? And that's the main idea here. So you also see that, in a way, you get more direct connection through the network, and you save some connections, right, if this is really working. So the transformer is also called like that because it transforms a sequence into another sequence. There is no convolutions, no recurrence. In fact, we don't need to think now at these time steps anymore. We can give it a sequence. It's highly parallelizable. It captures long-range dependencies, and it's generally working very, very well for sequence information. And here you see the key from the original paper. We propose a simple network architecture, the transformer based solely on attention mechanism, dispensing with recurrence and convolutions entirely. So it was pretty, a revolution in a way. Now, how does it look like? It's kind of a scary beast. Indeed, we have a lot of details in this architecture, and we will unravel this beast now. One thing remains is you have, again, an input that you encode, and then you send it to the decoder to do the decoding. Okay, so the original formulation of the transformer was, in fact, an encoder-decoder model. Let's look at the key overall idea. So we have a sentence, and we encode it. We get first the input embeddings, and then we have a series of layers. Oh, let me go back to this. So this is a transformer block, and you have several of those. And now I'm simplifying this block as one of the states. Okay? So here is one of these blocks in this green box here. And now when we're doing encoding, what we have is self-attention. We're looking in this state here at all the previous input states, or here we look at the previous encoder states in order to compute the next state. Okay? And for that we use self-attention. And once we have encoded the sequence, we can do decoding. And again, at the decoder side, we essentially, machine translation is fun. Okay, we are here at this stage here, la traduzione. So we are looking again at the decoder itself. So what is currently happening at the decoder stage, right? Similar to the RNN before. So you would have encoder, decoder, but with self-attention only. And in addition, you also need to look back at the encoder. So that's why you also have encoder-decoder attention that looks across the two. Okay? And with this way, you are going further and decoding one word at a time by looking at the decoder and back at the encoder-decoder states. Okay? All right. Is the key idea clear? Right. Now, let's look at the building blocks. Let's open up this box and look at all these pieces that go into this computation. And for that, we need to look more in detail at this attention computation. Because to compute the attention, we need a scoring function that we heard before, right? The function A. They use the dot product, which is simple and fast to compute. But they introduced, so here is the dot product. The idea of the dot product is a way to measure the similarity between the representations, right? Two representations, you measure the similarity, pairwise. But for high-dimensional vectors, if we do the dot product and then the normalization, we have trouble of very peaked softmax distributions, and that means we get small gradients. So they found that scaling the dot product was helpful. So in the transformer, we have the scaled dot product as the attention function. And with this attention function here now, we compare again queries and keys in order to compute the attention scores. Now, where do these query and keys come from? We could simply use the representations, right, itself, and compute all pairs of combinations, right? But a better idea, what they do is actually they learn multiple views. So they actually, in the transformer, we have query, keys, and values as key concepts in the attention mechanism. So you can think of this as the hidden representation being used 3 times, giving you 3 different views. Okay? And now, if we are here at machine translation, we have this as query. We want to compute the similarity with the key on this one, and on this one, and on this one, and so on. And so we compare the query with the key 1 here, and then use the value, which is again the, where is it? Where's my mouse? Yeah, here. We use these two to do the similarity calculation, and then use the value to do the weighting and normalization. And that gives you then, for this query, the similarity with all the other vectors in the sequence. Okay? And this is the key idea here. So you transform each representation into some learnable query, key, and value vector. And these are parameters that you learn. And so the query again asks all the key vectors in the sequence whether they are relevant. This is then resulting in these attention scores. Asking in this transformer is the scaled dot product. And then you compute new contextualized token representation by the self-attention as the weighted average over all value vectors. So the value vectors are used to do the computation using the attention scores weights. Okay? So again, what happens? We compare query 2 here with key 1 and all the others. Oops. Yeah, and do this for all the other parts in the sequence as well. All right, but we are not yet there yet, because now if we do this, we get a softmax, right? In the end, if we do the query Q2 with Q1, with itself, with this one, we get 4 values, 4 attention scores. And maybe the first one is indeed the most important one, machine for translation. But we are putting a lot of information into that single attention calculation, right? Does that make sense? And so one of the key ideas of the transformer was actually to do multi-head attention. And why do we want to do this? Because different parts of the input can be useful in different ways to disambiguate. Okay? You can think of this as attention is looking at the important information for me to help disambiguate or translate or whatever. And if I have these sentences, this is a nice example from Graham. I run a small business. I run a mile in 10 minutes. The robber made a run for it. The stocking had a run. It's all about run, right? But what is the difference between the first 2 sets and the last 2 sets of sentences? It's different part of speech, right? It's a verb versus noun. While if you look within, say, a verb, it really depends on the context what this verb is used for, the semantics, right? So intuitively, you would like to look at different parts of the input with some different lenses almost. And that's why we use multi-head attention, where the idea is to duplicate the effort. So you have different heads that do the same attention calculation with different sets of parameters. Okay? So now you learn one attention head, which has query key and value parameters, and you have a second attention head that you randomly initialize and do the network figure out the parameters so that it would then give you, in the sense, 2 different attention sets that you can then combine and run through a linear projection to get, finally, the multi-head attention output. So you're not only having one set of attention weights, but multiple. You run them through a projection in order to compute your new output in the layer. And so this is called multi-head attention part. Yeah?
It's not only 2, it could be more. It's not only 2.
Yeah, exactly. And this is now, indeed, this is not only 2, but in the original architecture, they had, I think, 8 in the small and 16. So you have multiple sets of these heads, but you have multiple. So that's a multi-head attention idea. Exactly. Great. So we have multi-head attention. And here is an illustration also why this would be helpful. So here the different colors give you the scores, attention scores from different attention heads. And you see that the different attention heads look at different parts of the input sequence to do the decoding. So multi-head attention is the first bit. There's 2 more. One is add a norm. So there is some more ingredients that we need to cover. So I will just go quickly. There is actually a layer normalization also happening so that you normalize the values in the layer. And there is also residual connections happening, so that that we saw before. And that's everything that happens in the encoder, and that finally you send it to a feed-forward neural network, which really looks at all the representations together and normalizes them again, finally. And so this one thing here with multi-head attention, adding normalization, feed-forward neural net, and another set of add and normalization is one layer in the transformer architecture where you can have several of those stacked on top of each other. So we have encoded now the sequence, but what about the decoding? The decoding then has a little bit of additional concepts to cover. We have looked at self-attention in the encoder now, but when we move to the decoder, you have again 2 types of attention here, because you need to think of, in the encoder we have access to the whole sequence, and in the decoder we only have access to the previous tokens. So we need what's called mask self-attention, where we mask out the future tokens, right? Because when we use the model, we don't see them. So we should also train them in this way. So we use self-attention on the decoder side, but mask it up to the point where we are currently. And that's called mask self-attention. And then finally, there's also the last bit, which is encoder-decoder attention, which connects the two, encoder and decoder. So this captures self-started translations, and now the query comes from the decoder, and the key and value comes from the encoder. So this is a bit back to what we saw before from the RNNs, right? And with all this together, we have covered, and also called cross-attention, we have covered the main big parts of the transformer architecture. Okay, so what did we see now? We have an encoder with self-attention at the input. We have a decoder, and we now can use that to decode the sequence. Are we still missing anything?
Sorry, the second self-attention should be cross-attention.
Yeah, that's here. That's here. Encoder, decoder attention. That's here. Both self-attention and encoder, decoder attention. Right. So you see now you have a network which is fully made up of attention and feed-forward neural network parts and residual connect, like a lot of small pieces put together into this framework. But the key thing is that we no longer have these horizontal connections, right? Like compared to the RNN. We really had these direct connections all the way, all the time, which means we don't have order, right? We could run this essentially in parallel, right? So how can we keep track of order in this model? Does it? If I swap these words here now, would it be different? Would the computations that I get be different? No, right? Because all the computations are pairwise, right? There is no sense of order in this model. So the last bit of information that we are missing is indeed positional information. Does that make sense? We dropped the horizontal connections from the RNN between the hidden layers, but we really want the order to matter. So how can we get this back? And that's via positional embeddings. Because thinking back, the recurrency really naturally represents the order of words. Right, in the RNN, we process W3 after W2, after having seen W1, and so on. But in the transformer, we need an explicit way to represent a word's position. And an idea which is now used a lot is just mark the positions of the words. So say, going back here, this is the word at the first position, second position, third position, fourth position. And learn a representation of that positional information. First, 1, 2, 3, 4. Okay? That's the simple version, where you learn a representation of position for an index I for all of the indices, for a certain number of indices that you decide. Okay? So from 0 up to 512, I learn a representation of that position. And you can think of this in the same way as the lookup embedding layer that we had for word embeddings, now that they are just representing positions. Yeah? And that's the simple way to do so. And that's what's called position embeddings that we then simply add to our input embedding. So we have the input embeddings. Still, we use word embeddings, actually subwords embeddings. And we add positional embeddings that then change the representation so that the model learns where they are. There is a more advanced or different version of this. This is actually a whole topic that was investigated quite a bit. What are good position embeddings? I will not go into this topic now, But I want you to know that in the original transformer, they didn't use this simple way of using learnable parameters. They used a fixed way with sine waves so that they compute the relative, they compute the wave, the position. And that's how they also could use any kind of length, technically. But nowadays, a lot of the models are using, like the BERT model is essentially using this learnable representation. We get to that. And you need to add that to both encoder and decoder. And now we have a fully attentional network that since we learn this parameter, or we have this additional encoding, they are kind of aware of the order of the words. Yeah? Sounds crazy. It's like this. Yeah. All right. So putting it all together, we have an encoder, decoder. We have this inside this scaled dot product, which looks like this. And this is called the decoder transformer. So some core concepts that we covered are attention, self-attention, cross-attention, multi-head attention, mask attention, positional encodings, residual connections, layer normalization, and then finally the feed-forward neural layer. Right, so we have uncovered the model. And this was the original framework that has been introduced. But by now, we have different flavors of transformers, also for language. And in fact, another family of models are the decoder-only models, like the GGPs and Llama. They only work with input sequences. They don't split up. You don't have, like in machine translation, input-outputs, right? You have just decoder-only models, like GGPs. Or you have only encoder-only models, like BERTs. So they are for getting representations, and they are for getting generative models. And they are for everything in between. Encoder decoders, also T5 that can generate, or BART can generate. And just let me sum this up and then go into the BERT architecture. What did we get? We got from RNNs to transformers, we got much more parallelizable, faster networks with lower complexity, under quotes maybe. You get also shorter paths through the networks, through the attention mechanism. In contrast, RNNs are more cognitively inspired. So the original Elman architecture came also from if you have memory constraints. Transformers is like a result of really clever engineering, trying a lot of putting knowledge together. It's kind of a brute force. Why did they come up with exactly that architecture, right? Okay. But it works, and it's state-of-the-art in almost every NLP task. I want to add that the things we saw have, of course, developed further. There are new details that you see in Llama, new activation functions, new ways to train them, new ways to represent positional embeddings. All these bits and pieces change over time, but the same idea is still there. And I also wonder, I showed you RNNs in quite depth. Will we go back to RNN kinds of models, or is transformer all we need? I do believe we will go back, and we see already the beginnings of that happening right now. So it will be interesting times what's coming next. So in 2 years' time, what will be the lecture's content, right? But let's go a little bit more into more of the, I will go a bit quick here. So masked, in some concepts, so I want to just go into mask language model, free training, fine-tuning, and then end with prompting. So the encoder transformer, BERT, was essentially trained by looking at a sentence and just masking out some tokens, and you're predicting that token. So this masked language model objective became the BERT architecture. And the BERT architecture is an encoder transformer only. it assumes access to the complete sequence, and note that is not a generation model. It only gets you good representations. And so now we see that early models like BERT had 12 transformer layers, 768-dimensional word piece tokens. We didn't talk about this, but you don't have full words, you have subwords that you're using. 12 attention heads leading to 110 million parameters, which is nowadays tiny, right? If you think about it. Even BERT large with 24 layers had around 340 million parameters. Then after BERT came Roberta, because I didn't talk about this, but the objective of BERT was actually 2 objectives. Let me show you. Where did I have it? So you didn't have just this task of masked language, masked token prediction, but you also had a second task that you predict with BERT, and that's multitask. You're not just training for one task, but for 2 tasks with the same architecture at the same time. And so Roberta dropped one of these tasks and just used masked language model, while BERT essentially used used sentence prediction. So it actually got 2 sentences as input. My dog is cute and he likes playing with the separator tokens, and tries to predict if the next sentence follows the previous one. That's one task. And masking out some words. Okay? And as input it had token embeddings, what we saw before, but it also had the position embedding. So now here we really have just the integers to represent the positions, but it also had segment embeddings, and segments are just 2 embeddings that either say you're on the first segment or on the second segment, and all these 3 together are fed into the BERT model for learning. Okay. So the 2 objectives were masked language modeling and next sentence prediction, learned on raw text. And later on, Roberta was essentially trained on more data, but no next sentence prediction. And it also did something called dynamic masking, where it changed where it was masking the tokens instead of keeping them the same. Right, let me go over this. So what do we get with BERT? We get a contextualized token representation. It's very similar to Elmo, right? But now with a transform architecture, without RNNs, and but very good token embeddings. And so BERT was really the start of a lot of development, which led then to LLMs today as well. What is BERT not great for? It cannot generate text. It's not generative or autoregressive model, but it was still used to fill in blanks. So you could still, if you mask a token and try to predict it, this is kind of still generating a token, right? But not a sequence, just a mask token. You could technically still use it, so to say. So this is mostly used for analysis tasks, but there was a lot of work in when this model came out. What does this model learn, right? And deciphering what especially internal representations were capturing, because a very good point of this model was that it's fully available. The whole weights and model was available. Even later, the training recipes became available. And this is much harder nowadays because often we don't even have access to the model weights and so on anymore. And there is a lot of interesting work that looks at BERT and what sort of information it captures. So there's one paper which called BERT rediscovers the classical NLP pipeline that looks at different, like from syntax, part of speech, up to semantic representations, showing that the model learns these concepts at different layers in the internal representation. Okay? So there was a lot of interest in this. Or here is a work by Max, PhD student of mine, who was looking at not layer-wise, but dimension-wise, what are these representations capturing with another method, and it's looking across multiple languages, seeing that the lower level tasks are actually using much more of the frequency spectrum, if you look at them like in this way, than higher level tasks, which look at less of this information. So a lot of this more interpretability work was done in these days. And but now we really move to pre-training, fine-tuning, not just BERT models, but really, really large models. So this is kind of the pre-training phase in general. Is you have a lot of data, you have a network, and you train typically, in early days, it was mostly an encoder system. You were interested in getting good representations, not so much about generating a language. And so in this frame from, say, roughly around 18 to 21, it was all about training language models as text encoders to get better representations. Why? Because these, based on like the Elmo work that I was showing you, these were powerful representations that then you could use for your task that you were really caring about. And so this framework was essentially then pre-train, fine-tune paradigm where you take a pre-trained transformer encoder typically, and then you further train it on your task-specific output. Okay, so task-specific text input. And why is this interesting? Because that enables a lot of what's called transfer learning. You could learn it. Maybe you had labeled data for your task for some language or some domain, but not for another language. So you could learn it on some language like English or German or so on, and then transfer the architecture to try to do prediction for language or domain for which you didn't have any Ys, you just had X's. Okay, so this was the kind of paradigm that was very prevalent, or is still very prevalent today, but it came from this original idea of pre-training encoders. And, but then indeed, people were traditionally interested in very different tasks. So we have language modeling or machine translation or a lot of analysis tasks. And then came the idea of, okay, can we actually build models that can do all of these together? And if you look at the types of tasks, they are very different, right? Some predict just one token, others predict entire sequences, others predict labels or structures or the slots for your digital assistant. So then the next generation or the next thing was really multitasking, where you try to build a model that can solve multiple task-specific outputs. And a lot of work was done in this standard multitask learning time. Oh, there's a typo. But the thing was that you had still task-specific layers. You had to think about, okay, now I have a classification hat versus I have a generation hat. So let's say I do named entity tagging, but at the same time I'm doing next word prediction. And that was helpful for named entity tagging, right? So you could combine it creatively in some way. But then the next shift was really, hey, why don't we do everything text? Why do we care about task-specific output layers? And so this next revolution was to treat everything as text to text, not having specific output layers, like just text in, text out. And that's really making you a very universal architecture. And that was also the idea from 2019 onwards, where you use a lot of pre-trained knowledge from the pre-training stage, but then transform everything into instructions and train a generative model, a text-to-text model. And with that, that was kind of when T5 was born, for instance. You no longer have task-specific hats, but you're just doing whatever task is doing via text-to-text format. Yeah? Right? And this is T5. It came with different sizes and was very, very powerful because it was shown to outperform BERT and other models. And yeah, there is a lot happening in this stage. I just want to end with some prompting and prompting caution, because now we really have text-to-text models, right? We have LLMs. And what we do with LLMs, we are typically not fine-tuning them anymore, but we are prompting them. And prompting is a way to give instruction to the LLMs that does not change their parameters. But in a way, you can change the prompt to get different outputs, of course, right? Give me an idea of some talk, or give me an idea of some talk as if I would be writing to the queen. And there is a lot of different types of prompting where you do not give them any examples, like zero-shot prompting, or you give some in-context examples, one-shot prompting, few-shot prompting, or more advanced techniques where you ask the model to think step by step. So let me just go through this quickly. So in zero-shot prompting, you don't give any examples. You just try and ask the LLM, okay, given this review, out of positive, which one would it be? And it gives you an output. Within context learning, you give a couple of examples and then ask the LLM for some output. And it has been shown that in context samples are helping the model to perform better. There is no learning involved. But these benefits also diminish if you give many more in context examples. And so another line of work came out of adding chain of thought prompting, where you ask the model to let's think step by step, and then you get more a breakdown. So a standard prompt would be, what's the size of a big lake closest to Verona? And you get an answer. But if you add, let's think step by step, then the model is triggered to walk you through the thought steps. I don't want to use thought steps because this kind of gives the model some, some reasoning, real reasoning, but that's how they are called. Or here's another example of chain of thought prompting, where the model gives you some explanation as well. And this has been shown to often help, in fact, the performance of models. Here is an arithmetic problem where it shows to be very helpful if you prompt it in this way. But let me end with some cautions thing, because now we're really in this world of prompting. And we've moved away from this nice notion of, we had nice tasks, we had well-split trained depth sets. We call it compartmentalized NLP view, to an LLM, and we just ask it anything, right? And so we get very powerful models, but they are less interpretable. And if I now talk about the task, right? I talked about bus tagging, NER, MT. These were typical NLP tasks. Now you can do everything with one LLM, right? And you can wonder, what is really a task even anymore, right? And how do we evaluate for a specific task? And indeed, it is really important to realize when you interact with these LLMs nowadays, a small change in the prompt can give you a large impact. A large impact meaning a very different answer. So here's a nice paper by Aline showing if you do minimal pairs, minimal changes to your prompt, like change from interrogative to imperative, what would happen to your output? And showing that you get very highly sensitive, a lot of variation. So the performance is really highly sensitive to this linguistic variation in the input. Or nowadays, it becomes very, very frequent to use LLMs for answering survey questions, which are typically posed in this multiple choice question answering style. So here is a question. The web was effectively invented by Berners-Lee in which years? And you give them the options. The advantage is now that you give, you can just look at the probabilities for these answer keys, and it's easier to extract the answer, right? The probability of A, B, C, D, you don't need to really parse the output. You just look at the first probability and look at what's the highest one to get it. But what was shown was, if you swap the order, you would not, the answer wouldn't change. It would still if you give A a yes and B a no, the model would give you this answer, and it might be giving you the same answer if you swap the mapping from A to your answer key. Okay, so really little details might matter a lot, and indeed this has been shown that a lot of these models have this what's called A bias, to just prefer to answer A or give higher probabilities to A, and this is really different from how humans would answer these multiple choice question answers, where there's a lot of more variation in there. And indeed, if you look at, so how this works is really you look at the first token logit and extract the one with the highest probability. But if you compare that to the output of the text, we were wondering this with my PhD student Shimpong here, this might not even match. So the way you extract your answer from the LLM might really be making a big impact on what results you're getting. So you see here that the text answer was actually more accurate than the first token probability in the sets of experiments. Or chain of thought prompting is another interesting thing. We saw that it helps us get better models, but we were wondering in this logic world, what about, is it actually valid, the reasoning? And we hand annotated these reasoning steps, and we saw that in a lot of cases, the reasonings you give are not valid, actually, if you carefully look through them. Okay. So, and indeed, if you look at this task, indeed, if you have these marbles and you need to identify whether the conclusion holds given these premises, is overall very difficult for the LLM. But if you look at the reasoning steps, so some models might really do very poorly at the validity of these steps in between. Okay, so what do we get from these models? We need to be careful. But then some people have said, well, can't we just, let me just go back to this slide. What about, this is a very tedious process, right? To do this manually is a lot of work, and that's the problem. We get LLMs, they're great at producing text, but looking at all the text is prohibited. So what about using LLMs to do evaluation? And that's a new evaluation challenge that comes out now. So we were looking also at just replacing human-given ratings with LLM ratings. So if you have a text and you need to rate it with some quality scores, right? This is typically done in summarization or NMT. And we look at models and how good they are. The key takeaway is that there's a lot of variability. And you might think, okay, let's just take the most powerful model, like a GTP4, to do this task, because it's hopefully very good. But the thing is, even a GTP4, while it is good in some tasks, it's not the best all the way. And there is a lot of variability in this model. So relying on LLMs for evaluation is not yet to be done. Right, and this relates to trust. So we need more trust into these models, and this relates to a lot of things we can work on in future. One is understanding better the behavior of the model, understanding better what goes into the models, better evaluation protocols. How can we devise better ways to know when a LM gives us good outputs and not so good outputs, or even knowledge about what we feed into the model. Maybe we can devise better prompting strategies or more informed information to give the model more knowledge about what we actually want to solve. And data routing, I want to just quickly show you this example, because in late 2022, when ChatGPT came out, and there was something like, oh wow, now it passes this traditional linguistic test of morphological inflection. Here's a VOOC, there's another one, there are two, and no, it turns out this was done only in English, and Leonie and David tried to do this systematically across different languages, and this is really a data contamination issue, that it's not the case that ChatGPT can solve this problem if you look across languages and look at words that it hasn't seen, because probably it has seen this sentence on the web a lot of times and learned this fact, right? So no, let's do better. evaluation, and there is also this nice paper by Bolocco et al. That showed that there is not just data contamination in the sense of training data out there on the web, like what we might expect there, but people using the web interface might indirectly leak data to these proprietary providers, not knowing that they might use this then for retraining their models. So there's also this indirect data leakage problem that has been pointed out this year. But given all this, I want to end with a positive note. I think now we have transformers, and we have a lot of exciting opportunities ahead, because this idea has been applied to vision, like making visual tokens, for instance. So a lot of other modalities become now much more easier to work with, and vision is one of them. But also speech, right? Speech was very difficult to work with. Indeed, historically, they diverged to different fields, right? The speech community have their conferences, NLP or text-based language processing has their communities, but now it's getting more easy as the technology converges to do also speech, for instance. And even more, there's a lot of other communities that are interested in these technologies and also using language as a bridge to their problems, like the robotics community as well. So they are interested in giving natural language commands to robots that then not only work with vision and text, but then they really need to interface with the real world to steer these robots. And or cars, self-driving cars. There's a lot of work in trying to use language to do better adaptation, better generalization, so a lot of interesting directions, right? And this is all built up with things we saw today, from original traditional models, language models, that are very important. All the bits and pieces that we saw from n-grams to more powerful RNNs, to putting it all together with attention to get better representations, to then this big important model, the culture transformer, which then led to LLMs and so on. And there is a lot to be done. So I think I'm just right on time, actually. So thank you so much. And if you have any more questions or want to talk to me, please just come to me. Thank you.
If there are any questions, we could take maybe one or two.
Yeah, we can take a couple of questions now.
Okay, based on your experience, if you have a text classification task,
Is it better to still use like a BERT-style model and then fine-tune it to predict the label, or instruction tune an LLM to do the same task?
Yeah, that's a good question. So the question is whether to use still a BERT-type encoder model or an LLM instruction tuned. No, there are tasks for which it has been shown that LLMs are not the best approach. For instance, relation extraction is one example, where you really want to have a structured output where have two words, what is the relation between them, or multiple, but binary relations is a typical problem. And there have been encoder-decoder models, but they're still very brittle, and then you have the problem of transforming the structure back into your original, which the verbalizer is not yet, So there are problems where just a simple encoder transformer is better and way easier also to deal with. So for simple text classification, pairwise classification tasks, it's still very good, yeah. So don't forget the past. Like, look back at the past to inspire the future.
Thank you.
Maybe also talk a bit about energy and cost.
Yeah, right. So indeed, Ian asked me about talking about energy and cost. So indeed, like now with LLMs, energy and costs has dramatically increased, right? BERT type of models are easy. They're also very fast. They are trained on commodity GPUs. So we need a lot of models. So if you think about LLMs, they are out of reach of just a single lab, typically, unless the lab is huge and very well financed. So we have huge energy consumptions that are also a concern, right? If you think about all the models on Hugging Face, and now only the English models. And I did this like a couple of 2 years back. It was already 30,000 English models, something like that. If you think about the energy that went into training or fine-tuning these models, it's a massive amount, right? So there's interesting ideas on how can we actually reuse existing models? How can we estimate transferability of existing models? How can we further train them with more parameter-efficient methods? Or how can we distill knowledge from existing models? All of these are interesting directions where there is work, but there's more to do to save environment and energy in future. And make more lean models, because scaling up is not the solution. Indeed, there was a nice slide by Graham who showed that if you have the transform architecture and to improve some of the components, it's not just scaling up by data, but also improving and making faster, better components that helps you to save energy. So we need to think also about that in future. Yeah.
I wanted to ask about the COT, about reliability of COT. So we can see that a lot of advancement in the recent years came from implicit COT, so just baking COT into training with the LLMs. But you also showed, and other papers and research shows that when we elicit COT from LLMs, it's either invalid reasoning or there is a bias leaking into that reasoning, or the answer is correct but the steps are invalid. Basically, what do you think about reliability of COT in terms of both training and evaluating LLMs?
Right. So the question is about the reliability of COT, chain of thought prompting. It's in both in training and evaluation, you said, right? That's a good question. I think there are some attempts so we need to give a really, really crucial aspect is better evaluation in general, so that we can trust what we get, right? And this is just so complex now because of all the things I've shown. But still, if we what did I want to say? If we think about COT and all the outputs, it's now I forgot what I want to say. Let me think about shortly. Yeah, we can, but I just want to think, what I see now happening, just, throwing other LLMs at COT's outputs, we are getting into some vicious cycle if we do this. And we should not do this. We should really be careful what we're doing. And maybe think about a multi-factored evaluation, right? That we take several views, or maybe back to logical systems. Maybe Mirella talked about this. There is also some that try to do semantic parsing of the reasoning steps. So some of these old ideas can be very, very, very helpful, I think, to connect to these problems. Or in general, modularity, but in the sense of diversity of models and evaluation schemes. And if we do that, then hopefully we get better outputs. Maybe COTs in a few days, that's no longer the thing to do because we have other better ways. Yeah, we will see what happens. But evaluation is key. So yeah, thank you for the question.
Hi, thanks for the nice presentation. So just maybe follow up to the, I'm here. Over here. So maybe follow up to the first question. So, and also this kind of notion of prompting and the issues that you outlined with prompting. So maybe a concrete example, right? So if, for example, one would want to do this multi-class question answering, right? So multi-choice question answering, and harness the power of, let's say, Llama 3, for example, right? In the example that you mentioned, you basically add the options for the answers in the prompt, and then you basically try to somehow extract the output.
Right.
Are you aware of maybe any labs or methods that apply some form of modifications to the LLM that make it more task specific, such that you can harness the power of Llama 3, propose a question, and maybe somehow sideways inject the options or this kind of additional information, and then as the output just basically get your single label, essentially, if you see where I'm going with that.
Right, you could technically also fine-tune your model, right? Further fine-tune if you have the ways to do so. Or there is also constraint decoding that you can apply, which you will hear more about later in the summer school. You force the model to output certain decisions instead of just relying on the log procs or trying to pass whatever output there is. So there are methods in this direction indeed. Maybe just also to add, there is not just chain of thought that we saw, but there's a whole literature on tree of thought, and you try to look at the whole possible branches of the model, tree of thought, and all these methods that came after that, where you have even a generator and a discriminator model. So you use several models to try to get more reasoning steps in as well, not just the output itself. All of this is interesting things to look at, but again, with a little bit of a careful eye, because I really would like to see more careful evaluation in future, that we know what works and maybe know what doesn't work, because that's often the missing bit and hard to get published. Thank you so much, everyone.